Today, examining the origins of the universe with the James Webb Space Telescope. It's the largest telescope ever sent into space, and its mission is to observe the birthplaces of distant stars, planets, and galaxies.
The James Webb Space Telescope may have solved a Puffy planet mystery. A surprisingly low reservoir of methane may explain how a planet around a nearby star grew weirdly puffy, according to new observations from the James Webb Space Telescope. The finding shows that planetary atmospheres can inflate to remarkable amounts without employing esoteric theories of planet formation, astronomers say. Hello, and welcome back to Z. This is another episode of Cosmic Mysteries. Today, we're diving into one of the universe's most intriguing puzzles, the mystery of puffy planets. And guess what? The James Webb Space Telescope might have just cracked the case. The Webb data tells us that planets like WASP 107b didn't have to form in some odd way with a super small core and a huge gassy envelope, Michael Line, an extrasolar planetologist at Arizona State University, said in a statement. Instead, we can take something more like Neptune, with a lot of rock and not as much gas, just dial up the temperature and poof it up to look the way it does. Discovered in 2017 by the Wide-Angle Search for Planets Consortium, WASP 107b, located roughly 200 light-years from Earth in the constellation Virgo, is among the lightest of the more than 5,000 exoplanets found thus far. Despite being nearly as large as Jupiter, WASP 107b weighs just 12% of the gas giant's mass, equivalent to only 30 Earths. For context, one Jupiter mass is equal to about 318 Earth masses. This planet is so puffy, the team says that its density can be likened to a microwaved marshmallow. From previous observations of WASP 107b's size, mass, and age, astronomers suspected the planet had a small, rocky core enveloped by a rich reservoir of hydrogen and helium gases. However, such a scenario failed to fully explain the remarkably bloated orb, which, despite the fact it orbits its star at 1/7 the distance between Mercury and our Sun, doesn't receive enough energy from its star to account for its cotton-like density. Alternatively, if the planet's core actually held more mass than expected, scientists say the atmosphere would have shrunk as the planet cooled over time, meaning it would have turned out smaller than what is observed. Now, using the JWST's data, combined with previous observations from the Hubble Space Telescope, two independent teams of astronomers may have solved the puzzle. In short, they discovered that methane in the planet's atmosphere is 1/1000th of what would be expected for this world. Because methane is unstable at high temperatures, astronomers say this surprisingly low amount is evidence that the gas from deep within the planet is mixing vigorously with cooler layers higher up. David Singh of Johns Hopkins University, JHU, in Maryland, who led one of the two new studies, said in the statement, "The fact that we detected so little, even though we did detect other carbon-bearing molecules, tells us that the interior of the planet must be significantly hotter than we thought. The extra heat likely comes from the fact that WASP 107b zips around its star every 5.7 days in an orbit that is not a perfect circle," the researchers say. The star's constant gravitational pull on WASP 107b, whose distance from its star keeps varying throughout, stretches and contracts the planet's profile, thereby heating it up. On Earth, a similar force by the Moon causes high and low tides. The planet's hot core, combined with tidal heating from its star, is also changing the chemistry of the gases deep within the planet. Zufar Rustankulov, who is a graduate student at JHU and a co-author of one of the two new studies, said in a statement from the university, "We think this heat is causing the chemistry of the gases to change, specifically destroying methane and making elevated amounts of carbon dioxide and carbon monoxide." In 2020, a team of astronomers, including Singh, detected helium in the atmosphere of WASP 107b, marking the discovery as the first time this gas was spotted on an exoplanet. The element, which was tentatively spotted on the world in 2018 before having its existence there confirmed 2 years later, was seen extending far out into space as a tenuous cloud. Because this planet's atmosphere is so far-flung, astronomers say ultraviolet radiation from WASP 107b star is slowly stripping the world of its air, about 0.1% to 4% of atmospheric mass every billion years, to be more specific, which results in a comet-like tail trailing behind the orb. Thanks to the planet's supremely puffy nature, astronomers can look about 50 times deeper into its atmosphere than they can for a world like Jupiter. Last year, for instance, JWST observations of WASP 107b's atmosphere showed it rained sand on the planet. The James Webb Space Telescope, JWST, may have unraveled the enigma surrounding puffy planets, a category of exoplanets that are larger than expected for their mass. These planets, often referred to as superpuffs, have confounded scientists due to their low densities, making them appear unusually large for their given mass. Understanding puffy planets. Puffy planets are typically gas giants with a radius much larger than anticipated based on their mass. This peculiar characteristic suggests a very low density, akin to cotton candy. These planets are often found close to their parent stars, leading to questions about their formation and structural integrity given the intense radiation they receive. The role of the James Webb Space Telescope. Launched in December 2021, JWST is equipped with advanced instruments capable of observing the universe in unprecedented detail, particularly in the infrared spectrum. This capability allows it to peer through cosmic dust and gas, providing clearer images and more detailed spectra of distant objects than its predecessors, such as the Hubble Space Telescope. Solving the mystery. Atmospheric analysis. JWST spectrometers have enabled detailed analysis of the atmospheres of puffy planets. By examining the light filtered through these atmospheres during transits, scientists can identify the chemical composition and structure of the planets. JWST has revealed that some of these planets have high-altitude hazes or clouds that could contribute to their puffiness. Thermal emission data. The telescope's ability to measure thermal emissions from these planets provides insights into their temperature profiles. By understanding the heat distribution, researchers can infer the atmospheric dynamics and potential mechanisms driving the inflation of these planets. Planetary formation models. Data from JWST supports refined models of planetary formation and evolution. The telescope's observations suggest that some puffy planets might have formed further from their stars, where it's cooler, and migrated inward. This inward migration could cause the outer layers of the planets to expand due to increased stellar radiation. Comparative studies. JWST's capacity to study a wide range of exoplanets allows for comparative analyses. By observing multiple puffy planets in different stellar environments, astronomers can discern patterns and deviations, leading to a broader understanding of the factors influencing their development. Key findings. Composition. Some puffy planets have atmospheres rich in hydrogen and helium, with traces of heavier elements. The presence of high-altitude clouds and hazes has been detected, which can reflect and scatter light, making the planets appear larger. Temperature effects. The extreme proximity to their stars leads to significant heating, which can cause the outer layers to expand. JWST's data suggests that thermal expansion plays a crucial role in the puffiness observed in these planets. Migration theories. The hypothesis that many puffy planets formed further out in their solar systems and migrated inward is gaining support. The differences in observed characteristics between planets closer to their stars and those further away provide evidence for this theory. Implications. JWST's findings on puffy planets have significant implications for our understanding of planetary formation and evolution. These insights help refine models of how planets develop in various environments and under different conditions. Moreover, understanding the mechanisms behind the puffiness of these planets can inform the study of our own solar system's gas giants and their formation history. In summary, the James Webb Space Telescope has provided critical data that may solve the mystery of puffy planets. Through detailed atmospheric analysis, thermal emission data, and refined planetary formation models, JWST is shedding light on why these planets appear so inflated, offering a deeper understanding of the diverse worlds beyond our solar system. To recap, the James Webb Space Telescope is solving the mystery of puffy planets by providing detailed atmospheric analysis, revealing the effects of intense heat, and supporting new theories about planetary migration. Stay tuned to Cosmic Mysteries for more groundbreaking discoveries from the James Webb Space Telescope. Thanks for watching, and put your idea and suggestions on the comments section.